Fiber optic cables have revolutionized the field of telecommunications and data transmission, enabling the rapid and efficient transfer of information across vast distances. These advanced cables consist of thin strands of glass or plastic, capable of transmitting data in the form of light signals. With their high bandwidth, low signal loss, and immunity to electromagnetic interference, fiber optic cables have become the backbone of modern communication systems. Fiber optic cables, also known as optical fibers, are thin, flexible strands made of glass or plastic that transmit signals in the form of light pulses. These cables are used for high-speed data transmission over long distances, making them a crucial component of our modern communication networks. 1. How fiber optic cables transmit light signals. The principle behind light transmission in fiber optic cables is total internal reflection. When light enters the core of a fiber optic cable at a certain angle, it undergoes internal reflection and repeatedly bounces off the cladding, effectively staying within the core and traveling through the cable without significant loss. Single-mode versus multi-mode fiber. Fiber optic cables come in two main types, single-mode and multi-mode. Single-mode fibers have a smaller core diameter, allowing for the transmission of a single light mode. They are primarily used for long-distance communication. Multi-mode fibers, with a larger core diameter, can transmit multiple light modes simultaneously and are typically used for shorter distances. Light sources and detectors. Light signals in fiber optic cables are generated by light sources, such as lasers or LEDs, and are received by detectors at the other end. The light signals undergo modulation, encoding data onto the light waves, which are then transmitted through the fiber optic cable. At the receiving end, the detectors convert the light signals back into electrical signals for further processing. 2. Advantages of fiber optic cables over traditional copper cables. Fiber optic cables offer far greater bandwidth compared to traditional copper cables. This means they can transmit more data over longer distances without experiencing degradation in signal quality. This high bandwidth capability is essential for today's data-intensive applications and services. Greater transmission distance. Due to the low signal loss in fiber optic cables, they can transmit data over much longer distances without the need for signal boosters or repeaters. While copper cables suffer from signal degradation over long distances, fiber optic cables can maintain their performance over hundreds of kilometers. Immunity to electromagnetic interference. Unlike copper cables, which are susceptible to electromagnetic interference, fiber optic cables are immune to such disruptions. This immunity makes fiber optics ideal for environments with high electromagnetic activity, such as power plants or industrial settings, where data integrity is crucial. 3. Understanding signal loss and dispersion in fiber optic cables. When it comes to sending signals through fiber optic cables, nobody likes a downer, especially when the signal loses its strength along the way. This loss of signal power is known as attenuation, and it's caused by a combination of factors. One of these factors is absorption loss, where the fiber absorbs some of the light energy, kind of like a black hole for photons. So, when it's all said and done, the signal that reaches the other end may not be as strong as when it started its journey. Modal dispersion. No, it's not a fancy term for getting lost in a daydream. Modal dispersion occurs when different light rays within the fiber take different paths, arriving at different times. Think of it like a group of friends who all leave a party at different times and end up taking different routes home. The result? They arrive at their respective destinations at different times. In fiber optics, this dispersion can cause the signals to become distorted and difficult to decipher, like those cryptic text messages from your friend who just discovered emojis. Chromatic dispersion. Chromatic dispersion is what happens when your red, green, and blue fibers just can't get along. Okay, maybe not exactly. It's actually caused by the fact that different wavelengths of light travel at slightly different speeds within the fiber. This means that by the time the light reaches the receiving end, the different colors may have gotten jumbled up, resulting in a blurred and confused signal. It's like watching your favorite movie with all the colors slightly shifted, not exactly an enjoyable experience. 4. Types of fiber optic cables and their applications. Single-mode fiber, SMF. Single-mode fiber, SMF, is like the introvert of the fiber optic world. It prefers to travel alone. This type of fiber has a smaller core size, allowing only one mode of light to propagate. It's perfect for long distances, as it experiences less signal loss and dispersion, making it ideal for applications like long-haul telecommunications and internet backbones. Multimode fiber, MMF. Multimode fiber, MMF, is the social butterfly of fiber optics. It can handle multiple modes of light at once. With a larger core size, MMF can accommodate different light paths, making it a popular choice for shorter distances. It's commonly used in applications like local area networks, LANs, video surveillance, and fiber to the home, FTTH, installations. Plastic optical fiber, POF. Plastic optical fiber, POF, is the laid-back, easygoing cousin of the fiber optic family. It's made from plastic rather than glass, which makes it more flexible and less expensive. While it may not reach the same bandwidth and distances as its glass counterparts, POF serves its purpose in applications like home networks, automotive systems, and decorative lighting. Applications in telecommunications. Fiber optic cables have revolutionized telecommunications, providing lightning-fast data transmission and reliable communication over long distances. Telecommunication companies use fiber optic cables for services like high-speed internet, telephone networks, and cable TV, ensuring that you can binge-watch your favorite shows and chat with friends without any hiccups. Applications in data transmission. In the digital age, data transmission is the name of the game, and fiber optic cables are the MVPs. They're used in data centers and server rooms to transmit massive amounts of information at incredible speeds. These cables are critical for cloud computing, online gaming, streaming services, and any application that requires rapid data transfer and low latency. 5. Installation and maintenance of fiber optic cables. Installing fiber optic cables requires a delicate touch, as they are sensitive to bending and stretching. Techniques such as conduit installation, aerial installation, and underground installation are commonly used to ensure the cables are protected and properly routed. It's like playing an intricate game of connect the dots without smudging the lines. Fusion splicing. Fusion splicing is the equivalent of a fiber optic marriage ceremony. It involves precisely aligning and fusing two fiber optic cables together to create a continuous path for light transmission. This technique ensures minimal signal loss and enables a seamless connection between two sections of fiber optic cable. Just like a matchmaker, fusion splicing brings two cables together for a lifetime of optical harmony. Connectorization and termination. When it's time to connect fiber optic cables to devices or equipment, a little thing called connectorization and termination comes into play. This process involves attaching connectors to the fiber ends and securing them to ensure a reliable connection. Think of it like plugging in your headphones. You want them securely connected to your device, so you can rock out without any interruptions. Cable testing and troubleshooting. Nobody likes a faulty connection, especially when it comes to fiber optics. Cable testing is crucial to verify the quality and performance of fiber optic installations. Specialized equipment is used to measure parameters such as insertion loss, return loss, and optical power levels, helping to identify any potential issues. Troubleshooting then involves pinpointing the problem areas and resolving them, so that the fiber optic system can shine bright like a diamond.